Welcome. So in this video, we are going to look at the concept of conjugates and how it can help us to evaluate limits. So let's first start with a problem that you may have seen already in high school, which is rationalizing the numerator of a ratio of expressions, one of which contains a radical. So in this particular example, we're rationalizing the numerator. So the numerator typically contains a radical, and we want to rewrite the expression differently so that the radical does not appear anymore in the numerator. So let's first start with 2 minus root 3 over 4. To rationalize the numerator, we are going to use the following identity, which says that a minus b times a plus b is equal to a squared minus b squared, which we call a difference of squares. So why is that useful? Well, if we multiply 2 minus root 3 by 2 plus root 3, so here our a is 2 and b is root of 3, so we're doing a minus b times a plus b, we are getting a difference of squares. In this case, 2 squared, 4, minus root of 3 squared, 3. So overall, 4 minus 3, which is 1. So if we want to rewrite 2 minus root 3 over 4 and remove the radical in the numerator, we want to multiply the numerator by 2 plus root 3. But to avoid changing the expression, we also need to multiply the denominator by 2 plus root 3 as well. And if I simplify the numerator, we get 4 minus 3, which is 1. And overall, the expression is 1 over 4 times 2 plus root 3, which is an expression that's equivalent to the initial one, but this time I have no radical in the numerator. However, as you can see, in the tradeback is that I have a radical in the denominator. We can do something similar if I have an expression that has a variable in it. And as you can see now, I want again to rationalize the numerator. And to do this, I will multiply a root of 1 plus x minus 2 by root of 1 plus x plus 2. But I have to do this in the numerator and in the denominator as well. If I multiply out the numerator, I get a difference of squares, which is in this case 1 plus x minus 4. If I simplify this, I get x minus 3 in the numerator. And as a surprise, we see that x minus 3 appears both in the numerator and in the denominator. And I will cancel those two common factors to get an expression which is 1 over root of 1 plus x plus 2. So in general, we call the conjugate of an expression of the type a plus b or a minus b the companion expression a minus b or a plus b. That is, the sign of the expression is changed. So if I had a plus at the beginning, the conjugate has a minus, and if I had a minus, the conjugate expression has a plus sign. In general, we use conjugates whenever a or b has a radical. So how does the concept of conjugate help us evaluate limits? Let's take a quick look at an example, which is the limit as x approaches 4 of root of 2 plus x minus root 6 over x minus 4. If we try replacing x by 4, we see that we have a limit of the form 0 over 0. So I could use L'Hopital's rule here, but I will show you how we could actually use the conjugate of the numerator to rewrite the expression differently so that we can evaluate the limit using the direct substitution rule. So if I multiply and divide the denominator, the expression by the conjugate of the numerator, I get in the numerator a difference of squares, which is in this case 2 plus x minus 6. If I simplify the numerator, I get x minus 4. And as you can see, I have a common factor of x minus 4 in the numerator and in the denominator. And if I simplify this, I get the equivalent limit, which is the limit as x goes to 4 of 1 over root of 2 plus x plus root of 6. Now, if I try using the direct substitution rule here, it actually works. I can replace x by 4 to get the value of the limit. There is no problem here, in other words, by replacing x by 4, but there was one at the beginning. So now we have an equivalent expression that does not have the problem we had at the beginning. So replacing x by 4, I get root of 6 plus root of 6 in the denominator. So in other words, I get 2 root of 6 in the denominator. And I could leave my answer like this, or I could also rationalize the denominator, that is, remove the radical from the denominator. Most textbooks do this, so this is why I want to show you what you might see in a textbook. So to rationalize the denominator, you multiply and divide by root of 6, so you get 12 in the denominator once you've multiplied by root 6, and you get root 6 in the numerator once you've multiplied 1 by root 6 as well. In our last example, we have the limit of root of 9 plus x squared plus x as x approaches minus infinity. So if you think of what this expression might look like if x would be a large negative number, you can see that the first term, if I look at the expression inside the radical, it's 9 plus x squared. So that means that if I take a large negative number and square it and add 9 to it, I'm going to get a large positive number. If I take the square root of that, it's still a large positive number. And x is just a large negative number. So overall, I have a limit of the form infinity minus infinity, which we call an indeterminate difference. In other words, it's the limit cannot be evaluated by just looking at this form. We have to rewrite the expression differently so that we can tell whether what the limit is like. It could be anything. It could be infinity, it could be 0, it could be any other real number. So we have to rewrite this expression differently in order to evaluate the limit, and our good friend here is the conjugate of the expression that we have here. So we multiply and divide by a conjugate. We get a difference of squares after expanding the numerator. So we get 9 plus x squared minus x squared. The terms x squared cancel out, so we just get 9 over root of 9 plus x squared minus x. Now, if we try replacing now x by a large negative number, root of 9 plus x squared will be a large positive number, and minus x, since x is large and negative, minus x will be large and positive. So the denominator actually is a large positive number as x approaches minus infinity. So we get a limit of the form 9 over infinity. And that's not an indeterminate form anymore, because as the denominator gets large and positive, the expression 9 over that number will become closer and closer to 0. So overall, our limit will be 0. Thank you for watching.